All right, welcome back everyone. This is a video to go over the solutions to the Unit 1 Personal Progress Check on AP Classroom. I thought I would just go through the problems and part of the scoring guide with you and just sort of describe some of the major ideas behind some of these problems and explain the solutions just a little bit. All right, so this first problem is actually an experimental design question. You're asked to think about an object rolling down an incline, and you're asked to sort of set up and describe an experiment that you could use to determine the acceleration of this object as it's rolling down the incline. One of the first things I want to point out as I'm going through this is that these numbers that are sort of circled in blue down here indicate how many points each part of the question was worth. All right, so the first part asks you to give an equation that includes acceleration and quantities that can be measured that you could use in your experiment here. So you can sort of get an idea from the equipment that's listed here. The things you can measure really come down to distance or displacement and time. So we have displacement, time, and acceleration to work with. So one of the major equations that relates those is this one. This is the displacement is equal to 1/2 times the acceleration times t squared. And if you want, you can include the initial velocity term here as well, and then just state that the initial velocity is 0 since you're releasing the object from rest, so we can actually ignore this part. But they will accept just this equation that I've got written down right here. So that's all you really need to do for the first part. So if we get measurements for the displacement and the time, we can plug those in and we can determine the acceleration. All right. So the next part, they want a little bit more detail on the exact procedure that you would use. So I want you to describe which equipment you would use and what you would measure. So if you go back to this equipment list, you have two options for measuring time, and we want a little bit more precision than a clock would offer, so I would choose the stopwatch. For measuring distance or displacement, we actually don't need the precision of something like a caliper. Something like a meter stick would be sufficient for this type of experiment, so those would be the two pieces of equipment that I would bring along. All right, so when we fill this out, we can measure displacement, maybe call that x or delta x, and you'd use the meter stick for that. And then we can also measure time, call that t, and we would use the stopwatch for that. All right, and then they want some sort of procedure here. I won't go through all of the details. You can look through the scoring guide as it's posted, but some of the main points, and actually I'll flip forward to it real quick. One of the things is they want you to mark off multiple distances. So you're taking multiple data points or multiple measurements, and the other thing is multiple trials. Remember, these are the two things that I sort of stressed early in the year: multiple data points and multiple trials. They actually don't require a whole lot here. They say 3 trials would be fine for this hypothetical experiment. So as long as you mention that you're going to repeat these trials, that would be an important thing that you want to make sure that you mention. All right, so basic idea is you mark the starting line, and then you mark at least a few other distances down the ramp, and you measure the time it takes the ball to reach each of those points, and then you repeat that a few times, and you get a list of delta x values and a list of time values, and you could put those on a graph and find the acceleration from there. All right, so next part is moving on to describing what you would graph to get a straight line that would be used to determine the acceleration. All right, so it would be helpful here to remember the equation that we said we were going to use. So imagine we have some table of values where we have delta x values for different points along the ramp and t values, the time that it takes the object to get to each of those points. All right, so if we just plot delta x versus t, that would not give us a straight line because we have this t squared in the equation. So we would need to linearize that, and there's actually a number of ways you could do this. one thing we could do is plot t squared on one axis and delta x on the other axis. So if we do this, we should get a straight line, and the slope will not be equal to the acceleration, but be related to it. So if you look at this equation written up above here, the displacement is equal to t squared multiplied by 1/2 a. So that would actually be the slope that we would have here. Okay, so main parts for part C, the main ideas, you want to make sure you have the horizontal and vertical axis correct, so that when you calculate the slope, you're taking displacement dividing by t squared and not the other way around. And then you also want to make sure you correctly interpret the slope. And I mentioned there are a number of ways you could do this. One other option would be to plot delta x and plot, say, 1/2 t squared. In that case, you would get a different graph, and here the slope would just be equal to the acceleration because the 1/2 is part of our horizontal axis. So there's 2 or 3 other options that they give you in the scoring guide, so you just need to give one of these options. All right, so moving on to the next question. Here it is. So the next question, part D, asks about what happens after the ball reaches the bottom of the incline. So now it rolls on a horizontal surface, hits a wall, and bounces back in the opposite direction. So you're given a couple of questions here. The first one, just a single point, they want you to draw an arrow that represents the acceleration of this object during the bounce. So that's happening in this figure here. All right, so things to remember here, acceleration is caused by force. So drawing the acceleration is sort of equivalent to drawing the force that's acting on this ball right now. And the force that causes the acceleration is the normal force from this wall. There's going to be a very large force pushing the ball back in this direction, and that causes it to change direction from moving to the right to moving to the left. So on our little diagram here, we would draw an arrow that shows the direction of the acceleration. So you don't need to label it, just draw an arrow pointing to the left. All right, next question. During this time, what is the magnitude, or is the magnitude of the acceleration greater than, less than, or the same as when it was rolling down the ramp? Okay, so some things you need to think about here. To get full credit for this, you need to explain your answer. So the first thing you can do is start by talking about how acceleration is calculated. So the definition of acceleration is it's a change in velocity divided by the change in time. So how does this answer our question? Well, if you think about the time involved in the two processes, when the ball is rolling down the ramp, this takes a longer amount of time. When the ball is in contact with the wall, that happens for a very short amount of time. So the acceleration caused by the ball colliding with the wall happens over a much shorter time period than the acceleration of the ball rolling down the ramp. So since the change in velocity is roughly the same, actually larger for the ball hitting the wall than it is rolling down the ramp, and the time interval is smaller, then the acceleration is going to be much greater when the ball hits the wall than it is when it's rolling down the ramp. So that would be our answer here. All right, so that's a quick overview of the first problem. The second one is a bit more concrete and quantitative. So this is the problem with the astronaut throwing a rock up on the surface of the moon. All right, so first question you're given here is to find the acceleration due to gravity on this planet X. All right, so we're given that the rock is thrown from a height of 100 meters. It's thrown upward with an initial speed of 15 meters per second. So that's these two pieces of information here. And then we have one more piece of data, which is that the rock takes 10 seconds to land down at the bottom of this cliff. So it's going to go up and then come straight down here, and it's going to land at t equals 10 seconds. Okay, so one of the first things you might do setting up this problem is just sort of set up a measurement axis here. So we're dealing with vertical motion, so let's draw a y-axis here. Let's put 0 down at the bottom of the cliff, and we'll measure y going up in this direction. All right, so we have an initial position, which is going to be 100 meters. We have an initial velocity, which is going to be 15 meters per second. Notice that's positive since it's going upward. And our acceleration is unknown. And then we have a final position, 0 meters, when it lands at the bottom, and that happens at t equals 10 seconds. So if we look at these variables here, an equation that involves all of these variables is this one here. So our position equals initial position plus initial velocity times time plus 1/2 a times t squared. So if we plug in our numbers here, this y on the left, you could call that y final. So that would be 0 equals 100 plus 15 times 10 seconds plus 1/2 a times 10 squared. So if we simplify this a little bit, we'll get 50a for this last term. So we'll get 250 plus 50a equals 0, and that gives us an acceleration of minus 5 meters per second squared. And that minus 5 just tells us that the acceleration is downward, which makes sense. All right, so question A, part 1, our answer is minus 5 meters per second squared, and that was worth 1 point on this problem. Second part of question A, also worth 1 point. How does the speed of the rock when it reaches the ground compare to the speed when it was thrown upward? All right, so for this one, there is another equation we can use. Velocity equals initial velocity plus a times t. So the initial velocity was 15. We have our acceleration is minus 5. T is 10 seconds. So this is 15 minus 50, which is minus 35 meters per second. Now you have to be really careful here because this is not asking about velocity, it's asking about speed. So the speed of the rock when it lands is just 35 meters per second. Remember, speed does not have direction, so it's never negative, it's always a positive number. So the speed is going to be larger when it lands than when it's thrown upward. As a general rule, anytime something is thrown up into the air, it's always going to return to its original height with the same speed, but in the opposite direction. So when this rock comes back down to the height it was thrown from, it's going to be traveling 15 meters per second downward, and then it's going to continue gaining speed in the downward direction, so it's going to land with a greater speed, and you could use that as part of your justification as well. All right, so most of the points for part B, for this question came in part B, so that was worth 5 points, and it asks you to give a paragraph response describing how this would play out differently if you did this on Earth rather than on planet X. So remember, on Earth, acceleration due to gravity is minus 10 meters per second squared. All right, so I will just show you their answer here. So they sort of list very clearly bullet points that they want you to mention. So was just mentioning what I said before, that the acceleration due to gravity is greater on Earth than on planet X. That right there is worth 1 point. So just always make sure you include the things that may seem obvious to you. All right, so you get 1 point for saying that the object will be in free fall for less time. Since there's stronger gravity on Earth, it's going to hit the ground faster, so time is going to be less. That's worth a point. And then you can also say that the maximum distance above the ground will be less. Again, this is due to the higher gravity. If you throw something up into the air, the stronger the gravity is, the less height it's going to gain before it starts to come back down. And then, since it's accelerating through the same distance, but at a greater rate, when it lands, it's going to have greater speed than it did on planet X. All right, so you can see this is sort of their general guidelines for grading this question. The last point was just for having something with a general paragraph structure, complete sentences, etc. All right, so that's pretty much it for this question here. There's a little bit of math at the beginning, so if you're rusty on the kinematics equations, if it's been a while since you've seen those, these would be good to review. And otherwise, I will post the scoring guide to its learning as well, so you can look over that at your own leisure if there's anything here that's still unclear. All right,